So thank you to the organizers very much for inviting our paper. It's joint work with Laura Veldkamp, who's at NYU Stern. I should mention that these are preliminary results, so the comments and suggestions are more than welcome, definitely. And before I go on, I'm compelled to give you the disclaimer. So here it goes. The views expressed herein are those of the authors and do not necessarily reflect the position of the Federal Reserve System. So it seems like for decades, macroeconomists have searched for shocks that could be considered potential drivers of the business cycles. And the recent advance in that quest has been to explore uncertainty shocks, modeled as volatility shocks. So many authors assume that a shock in their model, typically a technology shock, is drawn every period from distribution whose variance is changing over time. What we want to do in this paper is to take a step back and see whether we can try to understand where these shocks are coming from, how we can interpret them, and whether actually volatility shocks can be considered good proxies for uncertainty shocks. So whether volatility is a good proxy for uncertainty, or for that matter, any other measure used in the literature like dispersion, mean squared errors, whether they can be really considered good proxies for what we will call uncertainty, and I will be very precise about that. So to signal what we do, our measure of uncertainty is the conditional variance of the variable being forecast. What I mean by this is, for example, the uncertainty about GDP growth is going to be the conditional variance of next period GDP growth. We use this definition of uncertainty because it is this ex ante expected precision of agents' forecasts about future outcome that is theoretically relevant in determining option value. In particular, usually in the theories of the prescribed option value of weighting, the beliefs with higher conditional variances are going to be making agents postpone their investment or hiring decision. Now, the problem with that measure, as we discussed earlier, is that such measure is not readily available in the forecast data. So what we're going to do instead is we're going to propose some forecasting models, very simple ones, that are going to be proposed to fit certain moments of the observable data from the survey of professional forecasters. And then we're going to ask these models to inform us about what conditional variance looks like in these models. So this is going to be an exercise very much in the spirit of Bayesian forecasting with model uncertainty, as in Cogley and Sargent or Johannes, Lester, and Moore are using this kind of revisions in beliefs generated endogenously to see how they drive asset prices. So in our models, in all of those models, alternative models, the forecasting agent is going to be considering a model for the evolution of the GDP. That's all I'm going to be talking about here. Towards the end, I'm going to talk a little bit about the policy uncertainty. He's going to be filtering hidden states, estimating model parameters, and possibly also considering alternative models as data-generating processes. So we're going to take seriously Hansen's suggestion of thinking about how much statistical knowledge do we endow our agents within our models that we're constructing, as opposed to how much statistical knowledge of the world do we possess as econometricians estimating these models. So associated with each one of these forecasting models that I'm going to put on the table is going to be this series of conditional variance over time. And then we can take it and compare it with the existing measures of the commonly used as proxies of uncertainty. Okay? So what we'll find is that uncertainty shocks can arise as a real-time consequence of forecasters learning about model parameters, regimes, and possibly which model is the most likely to be considered a data-generating process, even if the underlying shocks are homoscedastic. The nature of these uncertainty shocks, however, depends on the nature of underlying risks and the type of inference problems that the forecasters are faced with. So what I mean by this is, depending on what we assume the agents within our models know, whether they are estimating on the parameters, but they know the data-generating process, for example, the resulting the resulting series of uncertainty, so that conditional variance over time is going to obviously differ. And then we're going to be able to go and compare it to, say, a series of Garch-implied volatility. So finally, I will argue that uncertainty seems to be really different than volatility, mean squared errors, or any other measures commonly used in the literature. So the name of the game here is going to be, I'm going to put on the table 4 alternative models. I'll show you how they fit the forecast data, and then I'm going to show you how the conditional variances look like, and I will compare them with other measures of uncertainty. But before I do that, let me just describe briefly the data. The only data that we're going to be using here, since as of now this paper is about uncertainty about GDP, is going to be the seasonally adjusted real GDP. And we're actually going to focus on the sample from 68, fourth quarter, because this is where we have the forecast data from the survey of professional forecasters to map to, okay? So the first model. We want to start with a very simple model, but a model where learning is meaningful, both meaningful and tractable. So first we endow our agent. We are assuming, we as a econometrician, assuming that the agent within our model is contemplating the following hidden Markov model. YT here is going to be describing the log growth rate of GDP in a given quarter. ET is just a simple normal random variable with variance sigma square. So notice that for the moment we're assuming it's homoscedastic, and that's actually going to be the case for the whole talk. ST is the random variable that is going to be following Markov process with the transition matrix whose entries are these QIJs, so the probability of switching from state I yesterday to J today. So what happens here is that, say that the agent observes the past realizations of the date of the GDP growth rates only. Since ST is the variable that is hidden from the forecaster, he wants to know whether fundamentally a high realization of this YT is due to him being in the high growth state in a boom, or it's just a particular realization of E. So because he wants to construct this forecast, so that's just predictive density, conditional on the whole history of observed data that he saw up to and including time t, he will first have to construct a belief about in which state he is. Okay? So let psi nt denote the belief about the state n that the forecaster holds in a given period. And so he will start with a certain belief at time 0, a prior about which state has realized, and he's going to be recursively updating these beliefs over time. So in that first model, we're going to assume straightforwardly that the only thing the forecaster is doing here is filtering the state, but he knows the parameters of the model. When I go to the data, I will tell you how exactly, what kind of parameters we give to the agent. And so then the expressions for conditional expectation and variance are the following. So here we just have the probability of tomorrow's state equal to 1. So I'm assuming from now on that there's only 2 regimes, okay? So that's just probability of tomorrow's state being 1, given that you enter with that belief about state 1, and the probability about tomorrow's being state 2. And these are just the drift parameters. And similarly for the variance. So notice that the variance is obviously, so the amount of uncertainty that this agent is faced with at every point of time is maximized when he thinks that the states are equally likely. Also, that variance, so for given parameters, sigma squared and mu1 and mu2. But when we go on later on and we ask the agent to estimate also the parameters, you're going to see that that variance is obviously the highest the dispersion in these mean growth rates. Okay? And so one thing that I want to at that stage define is, this is what we're going to be calling uncertainty. That's exactly the standard deviation of the conditional variance of that variable YT that is being forecast. And this too is something that we're going to be comparing to in the data. And later on I will define 2 more objects. So what we're going to call volatility is just the unconditional expectation of the error squared. We're going to be performing many estimations in the data to get that series of volatility and compared with our series of uncertainty that are going to be coming from these alternative models. Okay? Another thing that we're going to be looking at in the data is this absolute forecast error of the forecast. Okay? So in our model, since we're working with homoscedastic model, that's constant. But that's not what I'm going to be. That's something that I'm going to be comparing to from the data. So in the data, when I estimate a gauge model, those are just going to, this is just going to be a series of implied sigma squares, sigma t squares. 2y, correct. Absolutely. No. So in our model, this is just sigma squared, right? Well, the standard deviation of that. But in the data, let's see what it is in the data. Okay? Okay? Absolutely. So notice that conditional on S, uncertainty and volatility are going to be the same. But because the agent is faced with this inference problem, those are going to be different objects. Absolutely. Because when we go to the data, and we're going to want to estimate what that is in the data, we're going to estimate a gauge model. So the variance is going to be changing over time. Okay? At every point t, you're going to have sigma t squared. It's absolutely. So let me take a step back. So, yes, exactly. Okay, so let me explain. What we want to do is we want to put on the table the models that are going to generate series of uncertainty. The way we define volatility within our model is constant. So the learning on its own is going to generate time variation in uncertainty. Now we want to go, so that is constant in our model. But then we're going to go to the data, and we're going to see what the volatility in the data look like as implied by, for example, estimation of the gauge model, what people usually tend to do and feed into their equilibrium models. Absolutely. Absolutely. That's exactly the idea. So what I'm going to argue is that you'll see towards the end of the talk is that the reason why uncertainty and volatility is different. If we lived in the world where everybody knew everything, everybody knew the parameters, everybody knew the states, and the data generating process, there was one, then volatility and uncertainty and mean squared error for that matter would be exactly the same. Absolutely. But to show you that, I'm going to put 3 other models on the table to argue that that's not a feature of the specification of the model. So I'm just going to be layering different levels of different degrees of statistical knowledge that I endow my agent with, and that's going to be true. Okay, so I'm putting on the table now parameter uncertainty. So what happens is the agent is still filtering the hidden state, but now he also needs to estimate the parameters of the model, which in my model are just mean parameters, sigma, and the probability transition, the entries into the probability transition matrix. Okay? So the way the agent is going to be computing his conditional expectation now is he's constructing that state belief again, but now he has to condition on a certain, so we're going to do it at after the realization of every history. So after every history, he's going to be estimating his parameters. He's going to be having a vector of parameters, actually the whole distribution over that. So he's going to be integrating those parameters out, integrating out the beliefs, and constructing his conditional expectation. So the only problem with that a technical complication is that that object, the posterior distribution of parameters, is not readily available. So what we're going to do is we're going to employ the Monte Carlo methods to estimate it. So just very briefly how that works. So the general idea of Monte Carlo methods is to generate samples from the posterior distribution that we're seeking to characterize. The transition kernel of this certain Markov chain that is being constructed is just created by samples from a conditional distribution, for which I'm just going to be using the random walk. So what happens? After my agent observes a sequence of realizations of the growth rates, he's going to be doing the following estimation. He's going to start with some parameters theta with a prior over those parameters, and he's going to be then drawing that new theta from that distribution. So epsilon is just 0, 1. Tau, theta are just parameters that I can choose to optimize the performance of my sampler. So whether in this Markov chain that I'm trying to create, that would be the exact samples from the posterior distribution that I want to characterize, whether I'm going to accept that new draw or not depends on that acceptance criterion. If I accept it, that just becomes a parameter draw, a new parameter draw in that matrix, and then I set it to theta 0, and I'm doing that d times. So d has to be very big. And I'm doing that after every history, after every new data that arrives. So after every t in the real time, my forecasting agent is going to have the whole distribution of possible parameters. So samples from the posterior distribution. So he's able to compute this forecast and a conditional variance of the forecast. The third model. What I'm plotting here is the histogram of the GDP growth rates from 68 Q4 to 2011. I guess I'm just going to let you decide whether you see fat tails over there or not. What I'm going to do is I'm not going to also impose that on my agent. Instead, I'm going to ask him to see in the real time and learn. So he's going to be learning whether that same hidden Markov model has normal errors or t-distributed errors. I will actually show you, I will try to estimate the hidden Markov model with t-distributed errors, and I will show you what the results are. So in the third model, my agent in the real time is filtering the hidden states, learning the parameters, and is contemplating alternative models that can describe this underlying stochastic process. So how are we going to do it? A forecaster assigns a prior probability to one of the two models. So capital K is going to be just 2. There's going to be one hidden Markov model with normal errors, one with t-distributed errors. And in the real time, he's going to be just updating it using a Bayes rule. So everything that I showed you so far goes through. What happens is that the agent is computing the conditional expectation under each model, filtering the states, estimating the parameters, and he's just weighing those expectations by the posterior model probability weights. And the fourth model that I put on the table is the following. Our analysis so far has completely neglected the fact that the forecast data from the survey of professional forecasters has heterogeneity. Forecast dispersion is one of the inputs to other models. So another issue that we completely neglected is the fact that we're forcing our agent, we're behaving as if the agent was conditioning. When computing his expectation, he's conditioning only on the realization of the GDP that he sees. But obviously, in the real time, the agents within the model see much more information. So one of the ways of introducing heterogeneity that we're trying is the following. Now there's going to be many forecasters considering the following models. YT is still evolving as before, so there's a hidden Markov model that describes its evolution, but now each of the agents I is going to be receiving the following signal. That's going to be the signal about the future realizations of the GDP. It's going to have an idiosyncratic component, Xi, and so the idiosyncratic noise and the public noise. How am I going to create that signal? we're going to choose the variances of that signal. So we somehow need to produce that time series, give it to the agent, together with the realizations of the GDP growth rates, and have him learn in the real time again. So the way I'm going to produce that time series, so this is like a reverse engineering exercise. What we're going to do is we're going to match the variances of those shocks to match, in turn, let me show you. So we're going to choose the variance of the idiosyncratic noise to match the average forecast dispersion observed in the data, and the variance of the public noise to match the forecast mean square error. Okay? So that model by construction is going to fit those two models. And now the forecast of this forecaster is work by analogy to the previous one. The only thing that changes is now our agent is conditioning on the history observations of the growth rate and the signal that he sees. Okay? So the predictive distribution accounts for both of those histories of those sets of information. And my Monte Carlo methods are now going to be approximating that posterior distribution conditional on the history of realizations of the growth rates and the idiosyncratic signal. So we have 4 models on the table. We're going to bring them to the data. So what I'm going to do first is, probably. So one kind of, I guess, quick answer to the question would be to see how the precision of the average forecast compares to forecast dispersion measure, to see how, this is kind of the signal to noise ratio kind of exercise. If there will be additional precise information coming from what you're suggesting, then definitely that would be advantageous for reducing. I see. That is additional, yeah. Yeah, that's a very good point. Yeah, that's a much easier way of introducing heterogeneity, definitely. It's a very good point. Yeah, so let's bring those models to the data. So what I'm going to do here is I'm going to estimate these two hidden Markov models. One assuming normal errors, the other one t-distributed errors, and that's just maximum likelihood estimation. So the maximum likelihood estimations are going to be used in the following way. In the first model, where the agent is only filtering the hidden state, I'm just going to give these parameters to the agent. And he's going to be only reporting the state belief and his conditional forecast. In the model where the agent is also faced with parameter uncertainty, these maximum likelihood estimates are going to be prior means. And the way I'm going to set, so let me talk a little bit about it. So these are the maximum likelihood estimates for the two-state model with normal errors. So we have the recession state, minus 2.5%, quarterly on, this is the annualized rate. The boom, that's the standard deviation. And as you see, the maximum likelihood picks up the boom state as a more persistent one. The way I'm going to set the standard deviation of my priors is, because the recession state is less frequently visited, I'm just going to put looser priors on that. The estimation with the t-distribution, the number of degrees of freedom comes up to 4. That's pretty fat tails. The recession, the contraction is a little bit more severe. The boom, and again, the boom state comes up as a more persistent one. And these are the moments. So what I did, everything I told you about Monte Carlo methods helping me to construct the conditional forecast and variances of these forecasts, that's what they give. Let me start with that model. As I told you, the one thing that in all the remaining models, except for the model number 4, comes up really obviously is that mean forecast error is too high. And that's because those guys are really just conditioning on the past observations of the GDP growth rates. There's nothing else they can do. But also the correlation with GDP is really low because over there, the only way you're revising your beliefs if you have really... So we're missing out basically on all these small ups and downs because the agent revises his beliefs really strongly only once he sees really abnormal observation, whether on the up or the down. So another thing that all these models are actually missing on is the mean forecast. This is something that has been reported in the data as a bias. So what happens is the mean growth rate over that sample is something like 2.8, but those guys keep on underreporting, so they kind of behave as more pessimistic, right? So the mean forecast in the data is 2.24, and because neither of our models is even attempting to address that bias, then that's what's going to come up. But one thing that we can look at now is the conditional variances that are coming out from all these models. That's how they look like. So what I'm plotting here are the conditional variances associated with each one of the 4 models. The shaded areas are the recessions. And the numbers that you see here are the coefficient of variations of that series. So because they all have different means, what I did is I took the time series, I took its standard deviation, and I demeaned it so that they are comparable, so that I can compare the degree of time variation in all these series. So the model with the state uncertainty, the blue one, that series, as you see here, is varying only when the agent is observing really abnormal observation, right, in recessions, basically. Because the only reason for the variation in that series, where only the hidden state is being filtered, is the variation in the state belief. The model with state and parameter uncertainty. So for all the models where parameters are also being estimated, what happens is that there's a lot of variation in the beginning that comes up from learning. The variance is really going up. And then as the agent keeps on filtering the hidden state, but he's learning the parameters over time. So the level of this conditional variance is going to be coming down, okay? But it keeps on fluctuating. The highest coefficient of variation is obviously in the series with state, parameter, and model uncertainty. And that's because over there, even if the agent, so remember that he considers basically that it's both the model with the normal shocks and model with the t-distributed shocks that are plausible, and he's going to be weighting according to posterior model probabilities, which one is a more likely one. Over there, the abnormal observation of the growth rate is making agents still very uncertain because the outliers are very informative when we're working with normal distributions. But they are not giving us precise information when we have fat tails, right? And the coefficient of variation in our model with signal, it's pretty low, and that's because we're giving the agent this additional information, which is pretty precise. Okay? And the errors are normal, absolutely.
And then the others, then the green is similar, except in the normal periods you're learning about the parameter stuff with
So one thing that we checked was, remember that we have more GDP data than the forecast data. So what we did is we actually ran them, that estimation from 47 to see how much of that initial variation gets kind of smoothed out. So when the learning goes on for a little bit longer. And that is definitely true, but there's actually not much of it that gets dampened because this is the period where Y is also fluctuating a lot. And the only way that the fluctuation in Y gets fitted into my model is the way the agent estimates his parameters and the state belief. But there's only one variance. The shocks are homoscedastic.
So you get basically quite bad ones about the
In the model with the state uncertainty only, yeah, absolutely. But basically the message is, depending what we're assuming these agents within the model know, gives us different prescription about our implied series of uncertainty. So what I'm going to do now is to show you how the evolution of series that are commonly used as proxies for uncertainty look like over that period of time. And there's a bunch of them here. So what we did was we went to the data, and on that GDP data from 68, we estimated a bunch of gauge models. We chose the one with the highest likelihood. And there's actually not much volatility in there. So one thing that you see, I know that that picture has a lot of time series, but one thing that comes out of it is that the commonly used measures of volatility, estimated volatility on the data, are actually not that time varying. And in particular, they are not varying enough to explain variation in the forecast mean squared error or forecast dispersion for that matter. Okay? One thing I want to talk briefly about is one thing that we completely neglected for the moment is the fact that maybe this discrepancy between GDP volatility and what we define as GDP uncertainty is coming somehow through uncertainty about policy. Okay, so this is to say that maybe shocks to the underlying GDP process are homoscedastic, but GDP also depends on some variables that are heteroscedastic. So what we did is, our first take on it is, we went to the data, we estimated gauge model on the time series for federal government spending. Those are the results here. And the same for the interest rate. So these are kind of our proxies for uncertainty about fiscal policy, if you will, and the monetary policy. That evidence here is only supposed to be taken as suggestive of their existing the same puzzle as we discovered when we were talking about the GDP. What I mean by this is that the volatility that we estimate is never going to be enough to explain the variation in the mean forecast error, where the forecaster asked to forecast the federal government spending. And it doesn't seem so much of the problem when it comes to the interest rates, which kind of correlates with what you guys were talking about, I think. So the question remains, where do the policy uncertainty shocks come from? Can the same learning mechanism explain that time variation? Briefly, I'm going to tell you one more thing we did is, so we're talking about the uncertainty about GDP, but when we're constructing our models, the input to the model are something like TFP shocks. So just to show you what the results would be if I had the agents learn in the real time the evolution of the TFP process, allowing him to consider TFP being the same hidden Markov model with normal errors as opposed to TFP process with the t-distributed errors. And that's the conditional variances that come out of this model. So here you have the time variation in conditional variance, where the TFP growth is assumed to be this hidden Markov model with normal errors and with t-distributed errors. The coefficient of variation is much higher. Yeah, I guess I'm ready to conclude. One thing that I guess you discovered very early in that presentation is that if we're living in the world where everybody knew the data generating process, then definitely uncertainty will be exactly equivalent to volatility and to mean squared errors for that matter. But because that's not the case, then I guess that we should construct models to talk about uncertainty. Now, one salient feature of all our analysis, if you remember, is that the volatility of our measure of uncertainty, how the conditional variance varies over time, that's also not very big. So if anything, then we should look for, while we're building these models to understand uncertainty, we should probably look also for potential amplification mechanisms in equilibrium models. Having agents within the equilibrium model explicitly have preferences that explicitly account for these attitudes towards uncertainty resolution. One thing that we're setting out to do now is to see, so we kind of see now how this uncertainty compares to volatility. It would be really interesting to see how macro uncertainty compares to micro uncertainty. So we have this, we could construct the models, learning models, that could fit, say, something like the earnings forecasts, and see how those two so the conditional variances coming out from the individual firms learning their earnings compared to conditional variances coming out from this learning model about the GDP. I guess I speed it up.